In the previous lecture, we systematically learned about the operating principle and the features of buck converter. In power electronics, sometimes we also encounter the other types of converters, such as boost converter, inverter, and also rectifier. In this lecture, we are going to study how to derive different kind of circuit converter topologies based on the buck converter. And also we'll explain what kind of features do they have separately. So we first begin with the review of the conventional buck converter. First, let's plot the schematic of a typical buck topology. We have the input source and switch network. This is pole 1, this is pole 2, and the filter network. So L, C, this is the load resistor. Here is the output voltage. Based on the schematic of the buck converter, we can divide this circuit into 3 stages. The first stage is the power source. And the second stage is in the middle, which we call it the power conversion stage. The power conversion stage not only include the single pole double throw switch, but also include the inductor here. And the third stage, we call it the load stage. We put the filter cap together with the load stage. So for this very fundamental buck topology, we know that its conversion ratio can be written as M equals to the ratio between the output voltage and the input voltage equals to D, where D is the duty cycle, which means that the proportion of time when the switch is attached to position 1. So based on this very fundamental circuit, we can extract this power conversion stage. Here is the switch network 1, 2. Here is inductor L. And also we have the 3 terminals we denote as terminal A, terminal B, and terminal C. This circuit behaves like a 2-port network. AB formulate the input port. The voltage is V1. CB formulate the output port. The voltage will be equals to V2. So this is like we call this as a 3-terminal cell, right? Three-terminal cell. And the internal law is that for this 3-terminal cell, if we define D equals to the proportion of time when the switch is attached to 1 over 1 switching cycle, then we will have the following relationship, V2 equals to D times V1, as this equation indicates. So next, we can morph this circuit, try to derive different types of converter circuits. So first, kind of circuit manipulation we are going to talk about is the inversion. Inversion means that we exchange the input port and output port from the buck converter. So this side will have the load network. And the middle is still the power conversion stage. And the right-hand side is inverted, so we'll have the power source. Still, we denote this as node 1, node 2. So based on this inverted buck converter, the similar law is still valid. So we will have same, right? So V2 equals to D V1, where this is V2. This is V1. So we can see from the schematic. So here the V1 is essentially equals to the output voltage, right? Output voltage. And V2 equals to the input voltage. So we can insert VG, V2, V2, and V1 correspondingly. So therefore, we can derive that the relationship between the input and output voltage, which is M, equals to the ratio between output and input. So we will see that this equals to 1 over D. So since D is in the region from 0 to 1, right? So 1 over D is bigger than 1. So that means that the voltage gain is higher than unity. So the output voltage is boosted. So we call this as the boost converter. There is a convention that we usually define the D as the proportion of time the inductor is directly charged by the input source. So we can change this network a little bit by putting different notations to 1 and 2. So basically, we can exchange this power conversion stage by a different notation. So this is 1, this is 2. Here is L. If that conversion stage is changed by this stage, then the D will be modified correspondingly. So the modified voltage conversion ratio will equals to 1 over D prime. See, 1 over D prime. I'd like to say that those two expressions are essentially consistent. Okay, the difference is mainly because we put different name system to those two ports. So according to this voltage conversion ratio equation, we can plot the voltage conversion ratio versus duty ratio. So here is duty ratio. It exists from 0 to 1. Here is 0.5. And here is MD. So for boost converter, we will have such a profile. Initially, when the duty cycle equals to 0, the voltage gain equals to 1. With the rise of the duty cycle, the voltage gain will increase correspondingly. Overall, this curve is above unity. That explains why the output voltage is boosted. Okay. So that is the first trick we applied. And the second trick we are going to do is the rotation. So based on this conversion stage, we can rotate this conversion stage by 90 degrees. If we rotate it clockwise by 90 degrees, we will obtain such a switch network and the inductor, right? This is L. This is port 1. This is port 2. So after we're doing this rotation, we put this conversion stage into the middle to replace the old power conversion stage. We can plot the modified circuit correspondingly. So we'll have the input voltage source. Conversion stage 1, 2, and the right-hand side is the load with filter. C, L, R, and here is the output voltage V. So this circuit is derived from buck converter by rotating the middle stage by 90 degrees clockwise. So now let's look at what features does this converter have. So this can also have two operation modes, like in mode 1, which happens from 0 to DTS. Meaning the switch is attached to position 1, so we can plot its equivalent circuit. So here's input source. The L is shorted to the terminals of the input source. C is an energy storage unit which provides power to the load resistor. So we can see that for this condition, the VL equals to input voltage, right? Based on the KVL. Next, let's look at the operation mode 2, which happens from DTS to TS at steady state. So the switch is pushed to the position 2, so we can also plot the equivalent circuit. So here is open circuit. L is linked to the load stage. So CR, so the current here continues to flow through this network to charge the capacitance. So for this case, the inductor voltage, if we denote like this, the inductor voltage equals to output voltage. So we can apply the volt-second balance principle to this rotated circuit. So mode 1, the level is Vg. The proportion is of time is dTs. Mode 2, the value is output voltage. The proportion of time is 1 minus d Ts. At steady state, this should be equal to 0. We can easily derive the ratio between the output voltage and the input voltage. So M equals to V over Vg and equals to minus d over 1 minus d. So see that we have a minus sign here. This means that the output voltage has inverted polarity with the input voltage. So this minus sign indicates that this circuit is inverting. Then we look at this quantity, d over 1 minus d. This value could be bigger than 1 if d is bigger than 0.5. And it could be smaller than 1 if d is below 0.5. So it means that it can either boost or buck the voltage. So we call this as buck boost. So this circuit is named as the inverting buck boost. And we can plot its voltage gain waveform accordingly. D, M, D. So the MD will be negative, right? So it means that if D equals to 0, this value equals to 0. If with the increase of D, this value will increase in the negative direction. So here is 1, right? It can either buck the voltage or boost the voltage. So at here is 0.5. If D equals to 0.5, M equals to minus 1. So that's how we derive the inverting buck boost topology. Okay, we have erased the blackboard. Now let's talk about another way to manipulate the circuit, which we call it the cascade connection. The basic idea is very simple. Cascade means that we put two converters in cascade connection. So one in the front end, the other in the back side. So we can plot the block diagram of such a cascade structure. So same here is the input voltage source. And here is the converter 1. We denote its voltage conversion ratio as M1D. Then we put another converter in cascade structure. So here the intermediate voltage is denoted as V1. And here is another converter. Converter 2. The voltage conversion ratio is denoted as M2D. So we can see that both converters have the control variable as duty ratio, D. So this means that although they are two separate converters, they are synchronized controlled. And the output port, we have the output load resistor. So the voltage here is denoted as output voltage, V. So according to this structure, we can see that the converter 1 links the input port and the intermediate port. So we will have such an equation. V1 equals to M1D times the input voltage. Similarly, for converter 2, we have a similar equation. So V equals to V1 times M2D. So combining those two equations, we can see the overall conversion ratio. Of the entire cascaded circuit. M D equals to output voltage over input voltage. By combining those two, we can see that it equals to the product of M1 and M2D. So that's the basic idea how we establish a cascaded connected circuit. Next, let's look at one specific example, which is a buck boost example. Buck boost converter, we can implement the converter 1 by buck and implement converter 2 by boost. In the middle, we place a filter capacitor, so we can plot the circuit accordingly. Here is the input voltage source. So this is a buck converter. We cascade this converter. So here is port 1, 2. Cascade this converter with a boost. So here is the L1, L2, and here is the C1, C2. And here is the overall output voltage, V. So we can see here the second stage is a typical boost converter. So the middle capacitor here is actually a filter cap. So based on this cascaded converter, we can see that the M1 is a buck, right? So equals to V1. So V1 is voltage here, divided by Vg equals to D. And for the second stage, M2 equals to output voltage divided by V1. Since those two pair of switches are synchronized controlled, meaning that when this switch is touched to 1, so this switch is also attached to 1. So they would have the same D. So the M2 will be equals to 1 over 1 minus D. So together, we can derive that the MD equals to the product of M1 and M2 equals to D over 1 minus D. So this means that this D over 1 minus D can either be higher than 1 or lower than 1. So meaning that this is a buck boost. But there is no longer a minus sign here, so this is a non-inverting buck boost. Converter. Okay, so next we can try to simplify this circuit. Looks like this circuit has lots of components, 2 inductors and 2 capacitors. Can we simplify it? The answer is yes. So now let's do the circuit simplification. We can do 2 steps to simplify. Step 1 is that the filtering cap C1 can be removed. This is because we don't need to have an intermediate DC voltage. We only care about the input and output. So it can be removed. Step 2, if C is removed, L1 and L2, they are in series. We learn that from the circuit theory, if 2 inductors are in series, they can be combined by 1. So inductor L2 and L1 can be combined. We will arrive at a simplified circuit for the non-inverting buck boost. Here is the input source. Here is switch network. Here is the combined inductor, L. Here is another switch network, port 1, port 2, load network, CR. So here is the output voltage V. So this is equivalent to that one. So you might be curious about why. We can try to validate mathematically, right? We analyze its 2 operation modes, right? There are 2 operation modes. Mode 1 happens from 0 to DTS. We can plot its equivalent circuit. Both switch poles are attached to position 1. So the L is shorted by input source. And the output port, the capacitor provided power to the load resistor. So in this mode, the inductor is charged by the input source in this direction. So the current will rise. Right? Then we look at the operation mode 2. Which happens from DTS to TS. Again, we can plot its equivalent circuit. So switches are attached to position 2 here and here. So the input port is open circuit. Here is output port. So this time, the inductor current will continue to flow in this direction to charge the capacitor and provide power to the load. So we can see that in mode 1, the voltage across the inductor, so VL equals to VG. Mode 2, VL equals to minus output voltage. Given we define the polarity of VL like this. So we can apply the volt-second balance principle to L. So we'll write its volt-second in steady state, Vg dTs plus minus, right, V times 1 minus dt equals to 0 at steady state. So we can derive the M, which is voltage conversion ratio, equals to output voltage over input voltage equals to D over 1 minus D. See, this conclusion is identical to this conclusion. So this validates that our circuit simplification is accurate. So we kind of obtained a non-inverting buck boost by doing this cascade connection. Okay, we have erased the blackboard. Now let's talk about a different way to manipulate the converter circuit, which we call it the differential connection. Differential connection means that we have two converter modules together. Well, the output voltage is the difference between the two converters' individual output voltage. So we can plot one block diagram to illustrate this type of connection. So here is the input voltage source, Vg, to the ground. And we can have two converter circuit blocks. So here is the converter 1. So suppose its voltage conversion ratio is MD. So here is output voltage, V1. Here is common ground. And we also input this input source to a converter 2 here. So it's like their input are paralleled. So the voltage conversion ratio for this converter is denoted as MD prime. This means that the two converters are controlled complementary. So one is D, one is D prime. So here is the output voltage of converter 2, V2. Then we construct the output port, which is the difference between V1 and V2. So here is the load. resistor. And this voltage is denoted as the output voltage. Based on this schematic, we can see that the V1 equals to input voltage times voltage conversion ratio of MD VG. And V2 equals to MD prime VG. So the output voltage equals to the subtraction of V1 and V2. So which equals to MD minus MD prime input voltage. Suppose we differentiate them by M1 and M2. So here is M1 and M2. Then the voltage conversion ratio for the entire system, MD equals to differential output divided by the input voltage equals to M1D minus M2D prime. So that is a general example. So next, let's use a specific circuit to see what we can achieve. Again, we use our favorite topology, which is buck converter. So we see the buck differential connection example. Just replace those two blocks by buck, right? So input source, ground. So converter 1 is replaced by buck. Unit. So this is V1. Converter 2 is also replaced by complementary buck. Complementary means that the two terminals notation are exchanged. So here is 2, here is 1. So this voltage is denoted as V2. And we put the differential output here. That is the buck example. So regarding the converter 1, right, we will see that according to the Buck's principle, V1 equals to D times input voltage. And for the converter 2, we'll have V2 equals to D prime VG. So for the overall voltage gain equals to V over Vg equals to V1 minus V2 over Vg. Insert those two here, we will obtain 2D minus 1. This is because D prime equals to 1 minus D, right? So together they can arrive at 2D minus 1. So next, again, this circuit is a little bit complicated, right? With 2 inductors and 2 capacitors. We don't require a DC value here, right? Because we only care about the overall output voltage. So can we do the circuit simplification at what we did in the last board? The answer is yes. So we can do the circuit simplification. So we reorganize the circuit schematic and replot it. Here is the input source. Here is the switch network. This is position 1, position 2. And we kind of eliminate those two capacitors and put a filtering cap here. And those two inductors can be combined into one, right? Same as what we did before. So this is the combined L. And here is the load resistor. And we put a capacitor to serve as the filtering capacitor. So the output voltage will be right here. Let me use a blue chalk. This is the output voltage. And to the right-hand side, we have a similar switch network. So this is port 1, port 2. So this is the simplified differential connection bark. Now let's analyze its operation modes to see whether this simplification is correct. Okay. So we look at its two operation modes. For mode 1, means that the two switches are pushed to terminal 1 simultaneously. So mode 1 happens from 0 to DTS. The equivalent circuit can be plotted like this. So this is to 1, this is to 1, right? So L will be right connected to VG. And we have the output network here. C, R, and this is the output voltage. So for this case, it's like the inductor current flow in this direction, being charged by the input source. And next, for operation mode 2, which happens from DTS to TS. So the switch is pushed to position 2 simultaneously. So again, we can plot the equivalent circuit. Right here is VG. So it's like inverted. So the L is inverted to the bottom side, C. And then here is the R. So this time, because of the changing of the switch ports, here, the positive polarity here will appear to be bottom side. And the current flow direction will be in this way. IL, okay. It's like IL release its charge to charge the capacitor. So based on those two modes, we can write the expressions for inductor voltage. For example, in mode 1, inductor voltage equals to the difference between input voltage and output voltage. And in mode 2, the inductor voltage equals to minus the Vg minus Vout. See, based on the KVL, the VL will be equals to minus Vg minus Vout. So we can apply the volt-second balance principle here. At steady state, the volt-second of this inductor is equals to Vg minus V times the duration dTs plus minus V minus Vout times 1 minus C Ts equals to 0. So based on this volt-second balance principle, we can conclude that the voltage conversion ratio equals to ratio between V over Vg equals to 2D minus 1. See, this result is identical to this result. So this validates that our circuit simplification is correct. And we can plot this voltage conversion ratio graphically. So we'll see such a linear behavior. When the duty ratio equals to 1, the voltage conversion ratio equals to 1. When the duty ratio equals to 0, the voltage conversion ratio equals to minus 1. A middle point is when the duty ratio equals to 0.5. So we can see that this converter has output voltage in bipolar manner. So we can utilize this bipolar feature to implement a DC to AC conversion. So we call this as the inverter. Okay, and next, based on this inverter circuit, we can do the inversion for the inverter circuit to see what happens. As you can remember, we can circle 3 stages based on the inverter. So this stage, first stage, is the power source. And the third stage will be the load stage. The rest will be those parts. The rest will be the conversion, right? Power conversion. So we can apply the trick we learned before to do the inversion. So inversion means that we replace power source by load and replace load by power source. We will obtain such a inverted circuit. Here is the inverted power source. Here is the inductor. And switch network. position 1, position 2. And here is the load part. And here is another switch network. So position 1, position 2. This is the throw of the single pole double throw switch. So this is the polarity of the output. So after doing this inversion, we will get a inverted voltage gain. So for this inverted circuit, we will have the voltage conversion ratio equals to the 1 over this quantity. We can plot the profile of this voltage gain versus duty ratio. So for this circuit, again, we put the 0.5 in the middle. And here is 1. You will see that this is has 2 segments of curves. One is here. One is here. When d equals to 0, this value equals to -1, right? See, this is also bipolar output. By utilizing such a inverted circuit, we can realize the AC to DC conversion. We call this converter as rectifier. Okay, so in this section, we have introduced from the fundamental buck converter circuit by utilizing the basic circuit manipulation operations. We can derive different converters with different voltage conversion ratio and functions. Besides what we have introduced here, indeed, we can also derive some other more complicated converters. And the methodology here is consistent. And you can explore if you are interested after the lecture.